Hello friends, we have been considering the probability density function of the different distributions that we have looked into. Now if you could recollect, we have considered what a distribution is, what a population is, what a distribution is, and we have rather exclusively focused on three different types of distribution. One, we have referred to it as the average, or rather the normal or the Gaussian distribution. So the reason why we refer to it as the Gaussian distribution, or the reason why we refer to it as a normal distribution, is because when you consider the distribution of the population, so in our case we have been considering trying to understand, or we have been orienting our analysis or our study of these distribution based on a thought experiment wherein we have been measuring the lattice parameters of different alloys. And if these different lattice parameters that we have measured, if we are able to categorize it as ones with highest values, or ones with high values, the ones with low values, and ones with average values, what essentially you would find in the normal distribution is the population, or the number of alloys that assume the average value, is significantly greater than the ones that assume the low value and the high values. So essentially the population is highest when the lattice parameter is average, and as you move away from this average lattice parameters, the number of alloys that assume this average lattice parameters, they decrease. So that is what the characterizing feature about the normal distribution is. So the normal distribution will have a trend of this sort, and the highest population is observed at the average of the lattice parameters. So average value is assumed by the most of the members that we are considering. The most of the population assume an average value. So in this context, the most of the alloys, they assume an average lattice parameter, and therefore, and as you move away from the average, either in this direction or in this direction, towards the high lattice parameter values or towards the low lattice parameter values, what you observe is a decrease in the population. And this trend, or this sort of a distribution, or population distribution, is what we refer to as the normal distribution. And this normal distribution, as it is, it indicates the distribution of the population, number of alloys assuming a specific lattice parameters. And we saw that when we translate the scale that considers, or the way we represent it based on the population alone, to the probability, we were able to translate or arrive at something called as a probability density function for the normal distribution. So there is a specific expression that allows us to rather describe the trend in the normal distribution. So when you replace the population with that of the probability, we were able to arrive at a probability density function for the normal distribution, and there was a specific expression, and we saw that there is a specific expression that helps us describe the density, the probability density function for the normal distribution. So what essentially we are doing in this case is we are replacing the population with probability, so therefore we are including on y-axis, and this is the p of x, or the PDF of the normal distribution, and from this function we will be able to estimate the probability of an alloy assuming a specific range of lattice parameters. So when you are able to arrive at a PDF for a given distribution, it allows us to estimate the probability of a given population of a given member assuming a specific quantity, a specific value of a given quantity. So in this case, the members that we are talking about are alloys, and the quantity that we are interested in is in the lattice parameters. Now when we have PDF for any distribution, so we have considered normal distribution, and we have also considered exponential distribution, and when we have PDF for it, that is the probability density function for these two distributions, it is possible for us to estimate what would be the probability of a member assuming a specific quantity, a specific value. Now in this case, member is an alloy, and alloy wants to assume a specific lattice parameter, and we will be able to estimate the probability of an alloy assuming a specific lattice parameter. Now in case of normal distribution or Gaussian distribution, what we observe is the population is rather significantly higher when the values are, when we consider the values or the average values, and when you move away from the average values, the population, it progressively decreases. Now on the other hand, when you consider the exponential function, or the exponential distribution of population, what you observe is the population is rather concentrated on towards, or on the least values that members can assume. So again, in this case, the members are the alloys, and the least lattice parameters they can assume, they occupy on a scale or the left end of the scale, and the population is rather accumulated in that scale. And as you move away from this least value, the population progressively decreases. So that is one qualitative way of describing or graphically describing the exponential function. And we saw that it is also possible for us to replace this population with probability. The trend remains the same, and from that we are able to arrive at a PDF, that is probability density functions for the exponential distributions as well. Now, both the PDFs in both these cases, that is the normal distribution and the exponential distribution, it helps us estimate what would be the probability of a given member assuming a specific value. Now, in addition to that specific value, it is also possible for us to estimate the range of values, that is a value and a value below that. For instance, a given lattice parameter and all the lattice parameters below that. So what would be the probability of a given alloy assuming a lattice parameter and all the lattice parameters below that? So that can also be calculated from this function that we have arrived at from the population distribution. So essentially we have arrived at a function, refer to that as the PDF, that is probability density function. And this probability density function, it enables us to estimate what would be the probability of a given member assuming a specific value of a quantity. Now it is also possible for us from this PDF, using this PDF, to estimate what would be the probability of a given member assuming a range of values of a given quantity, and this range of values, it has a desired values and all the values below it. So if L1 is in our case the desired lattice parameter, it is possible for us to estimate the probability of an alloy assuming a value from 0 to L1. So if I consider an alloy, this is the desired lattice parameter, and when I consider the range, it ranges from 0 to L1. So if X is the variable, that is the lattice parameter the newly developed alloy can assume, so it should be less than or equal to 1, and it should always be greater than 0. So the probability of an alloy assuming this range of lattice parameter can be estimated from the PDF. This, when we treat it as a function, so we take the PDF, impose this condition, impose these boundaries, impose these bounds in the integral, and if we treat it as a function and we arrive at a function, such function is what we refer to as the cumulative density function. So cumulative density function, and that is what we see here. So depending on the PDF of the distribution, the population distribution, the corresponding cumulative density function would vary. So here, as you can see, this is the trend of the cumulative density function for the exponential function. We saw there is a different trend for the CDF for the normal distribution. So depending on the PDF of the population distribution, the corresponding trend in the cumulative distribution function would vary. So far we have seen two different types of population distribution. One is the normal distribution, wherein the population is rather largely concentrated on the average of the values that a member can assume, and as you move away from the average, the population gradually decreases. This is the characterizing feature of the normal distribution or the Gaussian distribution. In case of the exponential distribution, the concentration of population is on the least values a given member can assume, and as you move away from the least values, the population gradually decreases. So these are the differentiating features between the normal distribution and the exponential distribution. And the other distribution that we have to look is the Gaussian the gamma distribution. So what essentially we have in the gamma distribution, in contrast to the normal and the exponential, where in case of normal the population concentration was in the average, and in case of exponential what we have the concentration was in the least of the quantity a member can assume. In case of gamma function or the gamma distribution of population, this population can be concentrated anywhere on the scale. It can be concentrated, or it can be concentrated on the average. It will translate then into a normal distribution. So anywhere between the normal and the least and the maximum, the population can be concentrated, and as you move away from that concentrated region, the population gradually decreases. So in this case, in this example that you have seen, so that's in the illustration that is presented, here we have the mean, and here we have the least value, and the highest concentration of the population is here, so that is between mean and the least value. The a given member can assume. So, and as you move away from the mostly densely populated region, the population gradually decreases. So what essentially we have is, as opposed to the normal distribution wherein the population is concentrated on the mean, and as opposed to the exponential distribution wherein the population is concentrated on the least value a member can assume, the gamma distribution the population distribution in the gamma function or the gamma distribution can be anywhere on the scale. It can be between the average and the least. It can be between average and also the maximum. Anywhere the maximum population can be concentrated, and as you move away from the maximum concentrated point, so as you move away from this region, as you move away from this point here, either in this direction or in this direction, what essentially you would observe is there is a progressive decrease in the population. So what you have in a gamma distribution function or in a gamma distribution is rather there is a population concentration at a specific point, and it can be any point on the scale or it can be any point on the x-axis, and as you move away from that point, there is a gradual decrease in the population. So in this case, the scale we have considered the quantity is the lattice parameter. So there is a specific lattice parameter most of the alloy seems to occupy or assume, and as you move away from the specific lattice parameter, so in this case that desired lattice parameter is the LD, desired lattice parameter. So as you move away from this desired lattice parameter for the alloys we have considered, the population assumed or the population that assumes the other lattice parameters, they progressively decrease. That gives us the gamma distribution. So gamma distribution function is of this characteristic feature as opposed to the exponential and the normal distribution function. Now when we want to describe, so this is the trend of the gamma distribution. So what essentially the gamma distribution it indicates is the trend of the different or the population of the alloys that assume a specific lattice parameter. So that is what the trend it indicates, the gamma distribution trend, that is what it indicates. So there is a specific range of lattice parameter most of the alloys seem to assume or seem to rather possess, and that forms the highly populated region, and as you move away from this highly populated lattice parameter, the population gradually decreases. So this is rather the trend that you observe in the gamma distribution. Now when you want to translate this gamma distribution into a function, you need to translate this population to probabilities, and when you translate the population to probability, the trend it remains the same, and this is what gives us the probability density function. So similar to both the exponential and the normal distribution, when we translate and when we replace the population with probability, you end up with a function, and that function is what we refer to as the probability density function. Now, when we want to express the probability density function, this is where the role of gamma function comes into play. The reason why we refer to this particular distribution as the gamma function, because when we want to describe the probability density function of this particular type of a distribution, so this is a specific form of a distribution that we are talking about, and we want to describe the PDF of this specific form of a distribution. Let us forget about the name gamma. We have a distribution, and this distribution is given in this image here, and we don't know what name we have to attribute to it, and we have translated or we have replaced the population with that of the probability. Now we want to describe a expression, or we want to have a function that describes the distribution or that describes the curve in green. So we have a distribution of population, we don't know what name to associate it with it, but we have replacing this population distribution with probability, and when you replace it, you arrive, or rather when you replace it with probability and fit a curve over it, you get a green curve like this. Now you want to have an expression that describes this green curve, and when you want to have an expression that describes this green curve, it is found that when you use a gamma function, it becomes easier for us, it becomes more accurate for us to arrive at a function that would describe the trend in this green curve. So when you want to describe the trend, the curve associated with the distribution that is shown here, which is not concentrated at the mean or at the lowest or at the extremes. So we have the concentration of population between the mean and the extremes, somewhere in between the mean and the extremes, and we want to describe this distribution of population using a function, and in order to do that, we make use of the gamma function. So the gamma function helps us describe this trend in green, which rather describes a distribution wherein the population is concentrated not at the mean or not at the average or at the extremes, but somewhere in between. And as you move away from the densely populated region, the population gradually decreases. As you move away from the quantity that which is assumed by most of the members, as you move away from it, the population gradually decreases. When you want to describe such a trend, it is identified that, it is observed that when you use a gamma function, it helps us describe such a trend, and therefore we refer to this distribution as the gamma distribution. So the name gamma distribution comes, or we use gamma distribution, the term gamma distribution is used to represent this sort of a population distribution, primarily because when we want to describe the functions that we get out of it, the curve that we get out of it, when we want to describe the curve, we make use of something called as a gamma function. So what essentially is a gamma function? Let us look into the arithmetic aspect of it. What essentially is the gamma function? Now, gamma function essentially, it captures what we refer to as the factorial. Supposing you have a value, say n, that is a part of a real number, or rather a natural number. So a positive natural number. So you are considering a value n, and the n is a part of a natural number 1, 2, 3, 4 and so on and so forth, and it's a part of the positive natural number. Then the factorial, n factorial is written as, so you calculate n and n minus 1 and so on and so forth, or so on and so forth. So you can consider the product, and that is how you calculate the n factorial. Now what gamma function does for a member, for a quantity of the sort, you have a quantity, and this quantity can only assume a value that is a natural number, that a value of a natural number, a positive natural number, that is 1, 2, 3 and so on and so forth. So what gamma function, so gamma function of this quantity, this variable would be n minus 1 factorial. So we know what n factorial is, and the gamma of the n which is a positive number, a positive natural number. So the gamma function of a positive natural number is n minus 1 factorial. So n factorial will be the factorial of n, the factorial of n minus 1 would be the gamma function. So essentially what we have is, when you say gamma function of a given quantity, and that quantity assumes a positive natural number, then the gamma function of that quantity is n minus 1 factorial. Now essentially what gamma function, this is just a simplistic description for a specific case of n assuming, so this is rather a specific case of the quantity, the variable that we are interested in, assuming a value that is a natural number to the positive natural number. Now on the other hand, if we have a quantity like in the case of our lattice parameter, then our n, it is possible for the n to assume not only the natural numbers but real positive real numbers, be it rational or irrational. So meaning it can be 1.8, so 2, 1, so on and so forth, 2.737, so on and so forth. So any numbers are possible when you consider the lattice parameter. So unlike natural numbers, say 1, 2 and 3 and so on and so forth, in case of the lattice parameters, a given alloy can assume a lattice parameter that is not only a whole number but is also some sort of as a decimal associated with it. So in that case, when we want to have a gamma function, then essentially we cannot use such a description, such a simplistic representation. This is valid only for the positive natural numbers. So this is just to give you an introduction of what a gamma function is for a variable that is a positive natural number. On the other hand, when the variable is a positive real number, the gamma function in this case assumes a convoluted form, and it assumes, or it rather assumes the form of the function, and it is represented by 0 to infinity, again because we are considering the a variable that assumes a positive real number, like in the case of lattice parameters. So it will be x power n minus 1 and e power minus x dx. So when you have a variable and that particular variable is rather can assume a value of a positive real number, the gamma function for that variable is expressed in this manner. So it is possible for us to analytically show that these two are rather identical. So when you assume that n here is rather a positive natural number, then you will be able to show that this expression can be translated to this expression here. But nevertheless, what we essentially have here is, we have seen what a gamma function is. So gamma function extends the factorial of the natural numbers to that of the real numbers. So the factorial can be estimated, this factorial can be estimated only when the variable that we are considering is positive natural number, and when we want to consider estimate the similar factorial, when you want to estimate the similar factorial for positive real numbers, so this we will be able to do using this gamma function here. So gamma function essentially is a factorial approximation, a factorial operation. And now initially this factorial operation is only valid for the natural numbers, the positive natural numbers. Now when you want to extend it to the positive real numbers, we make use of the gamma function. Now again there is also a possibility of extending it to the whole of the real numbers, that is including negative real numbers as well. But for our discussion, let us focus on this particular description here, wherein the gamma function, it is helpful for us to describe the factorial for, or extend the factorial operations to the positive real numbers. We don't need when you have the factorial, it is required for us, or we can only handle the whole numbers, but in this case it is possible. The gamma function allows us to estimate the factorials for the positive real numbers, and it also, again, it can be, when you consider purely from a mathematical perspective, it can also be extended to the negative real numbers as well. Now, having seen what a gamma function is, it becomes rather straightforward for us to now express at least having understood what a gamma function is, having rather gained a notion of what a gamma function is, now it is possible for us to describe the probability density function of a gamma distribution. The probability density function P of x of a gamma distribution. So the probability density function of a gamma distribution, again, it is dependent on several parameters. So it is governed by the variable x, and it is dependent on, or it is influenced by several parameters like mu, beta, gamma and lambda. So the complete expression, the comprehensive expression for the PDF of the gamma function is of this form: 1 by beta, and we have this gamma function in lambda or gamma x minus mu. So rather it's a bit convoluted, and that's the reason I'm forced to I'm taking my time to write this down. Beta gamma minus 1 exponential of minus lambda x minus mu beta. So this is rather the comprehensive expression for the PDF of the gamma function. So one parameter that we are able to understand, or one characteristic feature of the PDF of the gamma distribution, is this gamma function here, which we have looked into. So this gamma function here is the characterizing feature of the PDF of the gamma distribution. Now the mu, again similar to that of this mu here, similar to that of the exponential function, it governs the location of your curve. So it is the location parameter. And the beta, similar to that of your exponential curve, it is rather referred to as the shape parameter. Again, you don't have to, of course, you don't have to memorize any of these expressions. I'm just giving you a foretaste of what this overall expression would look like. So that's the reason I have written it down. So it is rather a convoluted expression, and it has certain similarity. It uses a parameter that is similar to that of the exponential distribution, and as you can see, one key feature is we have introduced the gamma function. So that is the characteristic feature of the gamma distribution. When you want to have a PDF for the gamma distribution, we introduce this gamma function here. We have introduced that, and the other mu and beta. This mu and beta, we have seen it in the exponential distribution as well. So the mu, it governs the location of your curve, the location of where your curve is being positioned, and beta is the rather it governs this is scaling parameter, not the shaping but the scaling parameter. This is something that we have also seen in the exponential curve. So we have a scaling parameter on the location parameter that is similar to that of the exponential distribution. Now the other characteristic feature we have seen it to be the gamma function, and this lambda is something which we have referred to as the rate parameter. Again, the lambda, we refer to it as the rate parameter, and this rate parameter, it has the description, or it has a function that is similar to that of the rate parameter in the exponential function. Again, it governs the slope of your distribution function. So the three parameters that are involved in the description of the exponential function is also involved in the description of the gamma distribution function. So you have an exponential distribution function, and in that there are three key parameters that are involved: location parameter, scale parameter, and the rate parameter. And the location and the scale can be compromised, and the principal factor that governs the trend in the exponential function is the rate parameter. These three parameters are also involved in the gamma distribution function. Besides these three, we have one key component of the characteristic feature, which is the gamma function, and apart from that we have this gamma, and this gamma is nothing but, or it is referred to as the shape parameter. So we have these three that are part of, or that we have seen earlier, and that are part of rather the exponential curve. So this is a new one. This is referred to as the shape parameter, and again this is characteristic feature of, or it is characteristically associated with the gamma distribution function, the PDF of gamma distribution. And in addition to that, we have our characteristic gamma function associated with the PDF of the gamma distribution. So the comprehensive expression, the complete convoluted way of expressing the rigorous way of writing the PDF of the gamma distribution is of this form. Here you have the involvement of all the four parameters in addition to that of the gamma function. So we have seen what a gamma function is and how this gamma function is involved to describe the PDF of the gamma distribution. And besides this gamma function, we have four additional parameters, and three of these parameters are already, we have seen it to be a part of the exponential function. And now in addition to that, we have a shape parameter that is rather introduced to describe the PDF of the gamma distribution function. Now similar to that of, we may have made certain approximations to that of the exponential function, and those approximations were whether we assume that the mu, that is the location parameter, is 0. So the entire trend, it starts from 0, so the least values are rather close to that of the zeros, and we are focusing largely on the positive quadrants. So we are focusing largely on the positive quadrant. So the mu is 0, and it is possible for us also to assume that the scaling parameter beta is equal to 1. Now when we do that, when we introduce such conditions to the generalized or the rigorous expression of the PDF, when you introduce these conditions to the rigorous expression of the PDF here, so P of x, when you introduce these conditions to the rigorous expression of the PDF of the gamma distribution, so what essentially then we will have is P, the PDF of the gamma distribution, which is dependent on, so we have taken care of mu and we have taken care of beta, so still it will be dependent on lambda and gamma. So lambda is the rate parameter and the gamma is the shape parameter. So when you impose this condition, so this condition, like we have seen, rather it is a specific case of the generalized condition that we have assumed. So this is the generalized condition that we assume, and when you consider a specific case for it, when you simplify the entire expression and assume specific values for two of these parameters, still the PDF of the gamma distribution will depend on two other parameters. These two parameters are the rate and the shape parameters. So generally, when we talk about a standard gamma distribution, standard PDF of a gamma distribution, so PDF of a standard gamma distribution, what essentially we have is, as opposed to the exponential function, which is now principally governed by the rate parameter, in case of the gamma distribution, the PDF is governed by, in addition to the rate parameter, there is also something called as the shape parameters. So both these parameters, they dictate rather the standard form of the gamma distribution. So you have a gamma distribution, a standard form of it can be assumed, can be rather arrived at by these conditions here. So these conditions, they introduce a standard gamma distribution, And from the standard, when you want to describe the standard gamma distribution, it is possible for us to describe using these two parameters here. One is the rate parameter and the other is the shape parameter. So when you substitute these values here, what you would end up having is, so this expression here, the standard PDF or the PDF for the standard gamma distribution will be of this form. Again, the characteristic gamma function remains the same, and the rest will be of this form here. So this would be the PDF for, rather the PDF for the standard gamma distribution, wherein we have assumed the other two parameters have a specific value of 0 and 1. So this is the expression for the PDF of the standard gamma distribution, and from this expression we would be able to rather estimate the probability of, so when you have a set of members and the population of the set of members for a given quantity is distributed in the form of a gamma distribution, now it becomes possible for us from the gamma distribution to estimate the probability of a given member assuming a specific value from this PDF. So all you need to do is introduce an appropriate bound. So when you introduce appropriate bounds, when you consider the appropriate bounds, when you consider the area close to our desired value, when you introduce the appropriate bounds, you will be able to estimate the probability from this expression here. So both from this expression, when you have a rigorous gamma distribution, when you have a standard gamma distribution, from this expression here, what essentially you will be able to do is, you will be able to measure the probability of a given member assuming a specific value. Again, when I say bounds, since this is rather a continuous function, this is a function, and we want the way we are handling this function, or the way we are estimating the probability from this function is by calculating the area under this function, so the area under the curve, so to speak. So we need to have a definite bounds. So if x is our desired value, so x prime is our desired value, you need to create the bounds by including certain width to it. So h would give us the, would give you the width. So you have a desired lattice parameter value, you add and subtract it with a specific range. It can be depending on the overall scale that you have. This width might vary, so will vary of course. So what essentially then you would have is, you would create a region, and the area of this region, or the area that is rather within this particular section of the curve, can be estimated, and that will give you the estimate of the probability the given member can assume for, or a given probability of a given member assuming a specific value. So now again, from this function it becomes also possible for us to express the, or arrive at the cumulative density function. So once you have arrived at the PDF, so once we have arrived at, or once we have been able to express the PDF, the PDF lends itself to two different further estimation. One is the estimating the probability of an alloy assuming a specific lattice parameter, a member assuming a specific quantity. So that is possible to estimate it from the PDF. In addition to that, the range of values, that is from the least to a desired value, can also be estimated from. The range or summation of the probability can also be estimated from. So cumulative, it means we are summing up the different probabilities, and this cumulative can also be, the cumulative probability can also be estimated from the PDF by imposing the appropriate bounds. Now again, when we treat, the way we treat this cumulative boundaries, and we arrive at a function, we refer to that as a cumulative density function. So by imposing the appropriate boundaries onto this PDF here, we will be able to arrive at rather to these PDFs here. If we are able to introduce the appropriate bounds, then we will be able to arrive at the cumulative density functions for the gamma distributions. So what essentially we have seen is, we have seen three different types of distributions, and we have seen, or we have looked into the expressions for the probability density functions of all these three distributions. So the distribution, they primarily concern themselves with the distribution of the population. So they are not a function in themselves. And when we replace the population with the probability, we end up having a function. And depending on the distribution of the population, this distribution of the population is what lends itself to the the PDF or the probability density function, the trend remains the same. And when you have the probability density function, when you replace the population with probability, you will be able to arrive at expressions of this sort, discernible expressions of this sort, an expression that we could handle. And these expressions rather will allow us to calculate the probabilities, both individual probabilities and also the cumulative probabilities. So we have seen such PDFs, that is probability density function and also the cumulative density functions for the 3 different distribution functions that we have looked into thus far. So whenever we see such a trend in our observation during our materials research, now we will be able to rather express these distribution in the form of an equation. So that is one advantage of looking into this PDF. In addition to that, from these expressions, it becomes possible for us rather to estimate the probability of a member assuming a specific value. So not only it becomes possible for us to describe the trend, this trend here, but it becomes also possible for us to estimate the probability from this function, not only the individual probability but also the cumulative probability. So we have seen 3 different distributions, and from the 3 different distribution we have arrived at 3 different probability density function and also 3 different cumulative density functions. So once you have the probability density function, using the appropriate bounds, you will be able to arrive at the cumulative density functions. Now, what we have so far been considering is, again, to go back to the foundation or the premise that we have been considering, is that we have been focusing on a given setup. That is, we have been considering different alloys and the lattice parameters of these alloys. So whenever we considered the different distributions and the PDF and CDF associated with the distribution, we rather discussed in terms of a specific condition, that is, the variable x that we are focusing on, it assumes a value that is positive. And this positive value, it need not be a whole number, it can be any fractional number, it can assume any decimal values as well. So we have been discussing on a premise, and in this premises we are considering an alloy, and we are considering the lattice parameters assumed by these different alloys that we have built. And it means the variable that we are considering, the variable will always assume a positive value, and it will assume a positive value that need not be a whole number. So what essentially it means is, the variable that we are considering is a continuous variable. So when you have lattice parameter, it is possible for us to have, say for instance, 1.2, 1, 2 and 3, 4, so on and so forth, say 9. And it is also possible, say rather to make it simple, 8. It is also possible for us to have an alloy, and the lattice parameter of that alloy would be 2.1 and so forth, say several digits, 9. So even though it might appear to be discrete, when you place it on a scale, when you put this on a scale, what we will be able to see is that since we are considering so many places or away from the decimal points, it appears as though the values assumed by the alloys, the values assumed by the lattice parameter, the values that we attribute to the lattice parameters are continuous. So what essentially we have been looking into is a variable that is continuous in nature. So when the problem that you are working on allows you to consider or include variables, and that are not only whole numbers but that can assume the values that are with the decimal points, that are rather includes the fractional component to it, then essentially what you are dealing with is a continuous variables. Even though explicitly it may not appear to be continuous, but when you look into it, is possible for us to have lattice parameters that can apparently be continuous. Meaning it is not necessary that we have 2 alloys assuming these 2 values, but it is possible. The premise that we are considering allows us to do so. So therefore we can refer to that the variables that we are addressing as the continuous variable. Again, it is not necessary that we have 2 different alloys that are this much close to one another and that make the complete sense of the continuous term. But the premise, it's not that necessary, but the premise that we are considering, the nature of the lattice parameter, the nature of the quantity that we are considering allows such possibilities. So therefore we refer to such variables as the continuous variables. Now when these variables, for instance, instead of considering the lattice parameters, if we consider, for instance, the number of neighbors associated with the atom of a given alloy. So if we are creating an alloy, and for the different alloys, the number of neighbors associated with the atoms of the given alloy, it keeps on varying. For instance, for alloy 1, the number of neighbors for a given atom is 2, and the alloy 2, again purely hypothetically, and the number of neighbors for an alloy 2 for of an atom in the alloy 2 is 3, and so on and so forth, and it's n for alloy n. So you have constructed n alloys, you have built up or you have produced n alloys, and when you consider the number of neighbors for each of these alloys, so now when you consider the number of neighbors for the atoms in each of these alloys, for A1 it's rather 2, and for A2, for alloy 1, the number of neighbors is just 2, and and in the alloy 3, the number of immediate neighbors is just 3, and in the case of alloy 1, so the number of neighbors, so meaning you have an atom in a given alloy, and the atom is in contact with several other atoms, so that forms the neighbors. So you have an atom, and when you build an alloy, say for instance A1, this is the configuration of the atoms. So this is the configuration of the atoms. Now when you consider the immediate neighbors, it will be, so for this atom, when you consider the immediate neighbors, it will be 1 and 2, and when you consider the neighbors for this atom, it will be again 1 and 2. So therefore for this alloy, the number of neighbors for the given atom is just 2. Now let us consider the alloy 2. Now in this alloy 2, the atoms are arranged in this way. So the atoms are arranged regularly in this manner. So what you essentially then would find is the neighbors for this atom is 1, 2 and 3. So therefore the corresponding value is 3. So what then it is, so what essentially then we have is, we have considered n different alloys, and the number of neighbors for a given atom in that alloy can only vary in terms of the, or it can only range in terms of the positive natural number. It would not be possible for us to have the number of neighbors or the number of atoms surrounding a given atom in an alloy to be 1.2. Such real numbers are not possible. Such decimal or fractional values are not possible. So when you are considering, when the parameter, the quantity that you are interested in is the whole numbers, not the real numbers, but not the positive real numbers. So in this case, the example we have taken is the neighbors. So again, for the first alloy it is 2, second alloy is 3, so it can be repeating, so 2, 3, 4, and again the third alloy or the fourth alloy may have the 3, and so on and so forth. So you might have a definite set of neighbors that are possible, and it will be repeating amongst the different alloys that we have considered. So what essentially in this case we have is, in this case we have a variable that will not assume a decimal value. The variable will only assume a whole number, a value that is a whole number. Now such variables are represented by a positive natural number, and these are referred to as the discrete variables. So even in the simplistic premise that we have considered, when you are treating an alloy, when you are characterizing an alloy, when you want to understand an alloy, it is possible for us to estimate its lattice parameter, and in addition to the lattice parameter, you are counting the number of neighbors surrounding a given atom in an alloy. Now when you consider the number of atoms or number of neighbors for a given atom, the number of neighbors cannot be a decimal value. We cannot have one and a half neighbors, one and a half atoms touching, or an half atom touching an atom. So we cannot have an half atom touching another atom. So we have two whole atoms touching one another. So therefore the number of neighbors can only be a positive whole number, at least in the case that we are studying. When you have a variable that can only be positive and whole, that can only be a whole number, so such a variable we refer to as the discrete variables. Again, we are talking in terms, or we have considered a premise. So it is possible for us to have continuous variables, and it is possible for us to have the discrete variables. Now again, going back to our example, so supposing we have say 5 alloys, A1, A2, A3, A4 and A5, and the number of neighbors for A1 is 2, number of neighbors for A2 is 3, A3 is 2, A4 is 3, and A5 is 2. So these are the neighbors for the 5 alloys that we have considered. Now it is possible for us to create a scale. For instance, it is possible for us to create a scale that is 1, 2, 3, and we have 3 alloys that assume the value of 2. So that have 2 2 neighbors associated with its atom. So therefore we can have the population in this case would be the greatest in case of the 2. And in case of 3, here there are 2 alloys that have the neighbors, the number of neighbors to be 3. So therefore relatively the population will be less. And the number of alloys that have the population or the neighbors to be 1 is 0, so it will be here. Now what essentially we have now represented is, we have represented the population on a scale, and on this scale the population occupies a specific point, and that specific point is a whole number. So the population is associated with a discrete value. So in case of the continuous variables, we had to introduce the bins in order to build an histogram. However, in case of the variable, wherein the variable can only assume a specific whole number, so when the variable is rather discrete, so in such cases we no longer need the bins. The population can directly be represented. When you stack the population one over the other, we directly have the representation of the histogram. So we have seen what a continuous variable is or a discrete variable is. So continuous variables, all positive numbers, at least in this context they are all the positive real numbers. So here the discrete variables, all positive natural numbers, they are just the whole numbers. Now when you want to create an histogram for the continuous variables, we need to create a bin. In case of the discrete variables, we no longer need any bins because we are talking about the whole numbers alone. All that you need to do is stack the population one over the other, then you end up with the histogram representation. So once we have arrived at the histogram representation, what essentially we have is a population distribution, and from the population distribution it is possible for us to translate and arrive at the PDF for the population distribution. However, in the case of the discrete variables, the PDF has a new name to it, and we refer to it as the probability mass functions. So what essentially we have is, we have seen that the creation of the histogram is rather simplified when your variables are discrete. So when you have a discrete variables, the creating the histogram is rather straightforward. We don't need any bins. And now once the histogram is created, it becomes possible for us to rather fit a curve over it. And once you fit a curve over it, and then using this histogram, it is also possible for us to estimate the probabilities. And when you replace the population with the probability, you will be able to arrive at a function. And that function, when the variables are discrete, we refer to it as the probability mass functions. So the variables that we will be handling as once we are performing research on materials, it can be continuous or it can be discrete. So first it becomes important for us to understand if the variable that we are handling, is it a discrete one or is it a continuous one. So when the variable that you are handling is discrete, you no longer have to introduce a bin to create the histogram. So the histogram will appear by itself when the variable that you are handling is discrete. And now once the histogram is built, once the population distribution, we are able to arrive at the population distribution, then from the population distribution, it becomes rather straightforward for us to fit a curve, or rather it becomes, we are able to understand the flow of thought. We will be able to fit a curve over the population distribution and arrive at a function for it. And that function is what we refer to as the probability mass function. The probability mass function is equivalent of the probability density function when the variable that we are handling is discrete. So the probability density function is for the continuous variable, probability mass function is for the discrete variable. So with this we will wind today's lecture up, and we will try to gain some generalized understanding in the subsequent lecture. So again, what we have seen, to wind it all up, what we have seen is we have now classified the variables into two, discrete and the continuous variables. The continuous variables, it need not be like a smooth, so the premise that we are considering, the variable itself will allow the continuous variables possible. So therefore we refer to them as the continuous variables. The quantity that we are considering will allow for the continuous variables, so therefore we refer to that as the continuous variables. So we need not have such continuous values assumed by the quantity, but it allows for these values, so therefore we refer to it as the continuous variables. Now in case of discrete, the quantity that we are considering, in this case the neighbors, it will not allow for a continuous variables, a continuous change in the values. So therefore we refer to them as the discrete values. We cannot have 1.5 neighbors, we cannot have 2.5 neighbors. All we can have is one neighbor, two neighbors, three neighbors, and so on and so forth. So this type of variable we refer to as the discrete variable. And when you build an histogram, population distribution for the discrete variables, fit a function to it, and such when you want to express that function is referred to as the probability mass function. The probability density function is for the continuous variables, probability mass function is for the discrete variables. So we will build on this understanding in the subsequent lecture. Goodbye.